Thanks for the introduction. There has been a long-standing C++ folklore that says RTI and downcasts are horrible. And if you search online, you will find plenty of posts complaining about them. And sometimes they even make fun of them. That's how much they hate them, right? But is that folklore true? So today I want to get to the bottom of this folklore, and more importantly, can we dramatically reduce the overhead of RTI and dynamicast using link time optimization? So first, let's look at what dynamicast actually is. Dynamicast is a handy feature in C++ that allows us safely convert the pointers or reference between types. For example, let's see we have class dog, cat, and bird, and they all inherited from its base class animal. If we want to know that if the current object can fly, we can use dynamicast to check if the current object is instantiated from class bird. So what's nice about dynamicast is it is type safe, which you don't risk casting to the wrong type. And it helps us keep the code readable and maintainable. But here's the catch. The dynamicast works at runtime, and it depends on knowing the class hierarchy. So that leads to a big question, which is, how does a program know the type information in the runtime? And where does that type information come from? The C++ uses something called runtime type information to keep track of the type information during program execution. In this example here, the compiler generates RTI data for each class in the hierarchy. Each RTI data has two important pointers. One pointer points to its type name string, and another pointer points to the RTI data of its base class. At runtime, if we want to get the RTI data from the object, we start by looking at its virtual table. And the pointer of the virtual table actually is stored in the object layout. And from the virtual table, we follow the RTI data pointer to the RTI data. And from there, we know exactly what type the object is. Once we have understood the class hierarchy that is represented by RTI, we can go ahead with the dynamicast algorithm. Roughly speaking, we can think of the dynamicast algorithm as a depth-first search. So let's see we have an object that is instantiated from class D. And now we want to dynamicast it to the class B. So we start by looking at the class D's RTI data. But since the class D is not the type that we are looking for, so we follow the inheritance chain upward. And eventually, we reach the class B. So now we have found a match. And that means the dynamicast successes, and we get a valid pointer with type class B. So, but here is the downside. RTI is kind of infamous for eating up space. For one thing, each RTI data takes at least 24 bytes. And this is just a start. The type name string that it stores can be super long, like way longer than what you would expect. This is an example that is pulled from Chromium project. And the type name string itself is already 375 bytes. So now imagine that kind of overhead spread across 45,000 classes in Chromium. It adds up really fast. So now you can see why that folklore exists and why there are so many people hate them. Besides taking up space, the dynamicast also slows things down. There are a few reasons about that. The first is the dynamicast is implemented in the standard library, so calling it might cause the instruction cache misses. The second is, since it is a function call, so it acts like a barrier for the compiler optimizations. And most compiler optimizations, they cannot really kick in. And the third is the actual algorithm of downcasts is depth-first search, which is a linear time complexity. So downcast is safe, but it is definitely not cheap. And most programming language, like especially for the C++, they try to stick to the zero overhead principle. It basically says two things. The first is you don't pay what you don't use. But in reality, most RTI data, they get generated even if your program never uses it. And that's wasted space. And it totally breaks the spirit of zero overhead principle. The second is what you do use is just as efficient as what you could reasonably write by hand. But downcast doesn't hold up here either, because it is way slower than handwritten one. And we will show exactly how it slows things down in our evaluation results. So both RTI and downcast, they are not good. But if the compiler is supposed to be the main tool for squeezing out performance and the space for the program, why can't it just optimize them away? We found this because that in the real world C++ projects, most classes are scattered across files. And with the per-file-based compilation, each file gets compiled on its own. So the optimizer cannot see the full class hierarchy, and it also has no idea if this class hierarchy is inherited or not inherited from outside. So because of these uncertainties, it has to play it safe and assume the worst case across files, which really limits how much it can optimize. So we use link time optimization. With link time optimization, each source file first compiled to its intermediate representation. And then the linker put all these pieces together into a big LTO module. So now optimizing inside this big LTO module gives the optimizer a much bigger view, which now it can see the full class hierarchy. And because the linker also performs the symbol resolution, it can also figure out if the class hierarchy is inherited or not inherited from outside the LT module. So once we have the full class hierarchy, and we know that the class hierarchy cannot be inherited from outside the LTO module, we came up our new link time optimization, which optimized the dynamic cast into the simple membership check. For example, if we are trying to dynamic cast to the class B, actually it will only work for the objects that are instantiated from class B or class T. So that means at runtime, we just need to check is the dynamic type of the current object class B or class D. If yes, great, we return the cast pointer. If no, we return the null pointer. So it's a pretty straightforward idea. And so now let's implement it into the compiler, which instead of calling the dynamic cast that is in the standard library, we have the compiler generate the simple instruction sequences to do the membership check. So in our implementation, the compiler first arranges the class the classes in the class hierarchy using a pre-order traversal. And then the compiler generates instruction sequences to transform the dynamic cast into the membership checks. But sometimes we might have to check a lot of candidates. For example, here there are 3 candidates can be casted to class B. And our investigation also shows that for some dynamic casts, there can be over 15 candidates. So checking them one by one is not efficient. But thanks to the pre-order layouts, we can simplify each membership check into comparing their lower and upper bound in the layout, which gives us a constant time complexity. Besides optimizing the dimecast, we also want to cut down the space that RTI takes up. So first, we analyze the liveness of the RTI slot in the virtual table. And then we prune the slots that are never used. And once the dead code elimination optimization kicks in, all that unused RTI data get cleaned out. So now we have worked through our method. Let's see how it holds up in practice. To evaluate our benchmark, our optimization, we built a benchmark with over 50 million lines of code, which include both typical C++ project and the large-scale ones. But many large-scale projects, they disable their dimecast or use the custom RTI system. For example, Chromium, LLVM, and V8. So for these projects, we replace the custom RTI system with the standard dimecast. And we also evaluate our optimizations under two main types of link time optimization, which is full LTO and thin LTO. The full LTO is a heavier and more aggressive version that we talked about earlier. And the thin LTO is a lightweight alternative, which it is scalable and it can build fast. So it also has been the default LTO build for the Chromium project. So now let's look at the evaluation results. So we saw runtime performance improvement on all benchmarks in the full LTO. And on average, we achieved 1.4% performance improvement. Especially for the Solidity smart contract compiler, we got over 5% speed. And our optimization also cut down the binary size across the board. And on average, we achieved 1.7% code size reduction. And especially with the Envoy project, we reduced the code size by more than 4%. Now to see how well our optimization works on the large-scale projects, we picked LLVM. LLVM is a project that is heavily relies on the dynamicast. But to avoid the performance hit from the dynamicast, it builds its own custom RTI system. The upside is it is fast. But the downside is it is not compatible with the standard dynamicast. And it also requires a lot of manual code. For example, if you want to add a class into the LLVM, you need to implement the class-off method. And you also need to create a new unique class ID. And even worse, LLVM only uses 1 byte to represent that class ID, which means if the code base grows or gets refactored, there can be some compatibility headaches. So we replaced the LLVM's custom ITTI system with the standard dimecast. And the result is really brutal. It caused a 350% performance regression. So now more than 3 times slower for C++. That's a lot. And then we applied our optimization. And now we dropped the slowdown to around 5%, which is a huge improvement. And now let me wrap up with the key takeaway. So based on our study, the folklore about RTI and dynamicast are true. And they are one of the few C++ features that violate the zero overhead principle. So what did we do? We broke that folklore using our link time optimizations, which we restore the zero overhead principle for them by applying our new link time optimizations. For one, we optimize the dynamicast performance to match that of handwritten ones. And we also get rid of the unused RTI data, which now you are not paying space you don't even use. It's a step toward making C++ safer and faster, and without sacrificing the power it gives developers. Thanks for the listening.
Thank you very much. Really interesting project and talk. I guess I just wanted to check about the applicability of this. With link time optimization, am I right that this really only works when you have a full statically linked binary you want to run? And for example, if you have a binary that's going to work with shared object libraries and things, this doesn't apply.
Yeah.
Is that correct?
For the link time optimization, if you have the full project and you can get all of the source code and you build them together, then you can get a giant LTO module. Then you can analyze the.
But for example, I build tooling on top of LLVM, and I typically have the LLVM parts loaded as a shared object library. Could I apply LTO to that .so file?
Actually, in the dynamic linking, it doesn't work. But because our LTO module is only, if the class hierarchy can be referenced by the shared library, then our optimizer cannot kick in.
Yeah, okay.
But if your project is really care about the performance, you should put the LLVM source code into your project and build a large LTO module. Then our optimization can kick in.
Makes sense. Thank you.
Hi, I'm Singyun Nam from Seoul National University. Thanks for the great talk. And I really like the idea that you can optimize away the RTTI overhead by compiler optimization. But I have a question. So in order for this optimization to work, I believe that the distance between where the class is actually specified. So for example, you create a object of type D, and the place where you actually do the downcast for example, from type A to type D. So they should be really close, or maybe one function call away, because otherwise, in order to be sure that you can actually optimize the dynamic cast, you have to probably inline 3 or 4 function calls into that code. So how did you get to mitigate that issue? Or does it actually even work if the dynamic cast is 3 or 4 functions away, or maybe more, from the actual class instantiation?
Sorry, could you repeat your question?
Oh, okay. So what could your optimization do if the point of class instantiation is probably far away from the dynamic cast?
You mean you have a class and you want to dynamic cast into another class, and
if the function call depth from the point of instantiation to the dynamic cast is far away, so maybe you require several function calls, then I believe you cannot inline all the function calls into, so that you can be sure that you can optimize the dynamic cast from one type to another.
Yeah. If there is there are many function calls, then actually the inliner will inline all of these calls if it is good to inline.
So you actually do inline all the function calls?
Yes. Actually, yes. You can also regard it as we know what dynamics do, and we inline into our code and we optimize it.
Cool. All right, and then let's do one last question.
Hello, is this? Yeah, okay. Very cool work, thank you. My question is about the compile time overhead of this, because if you can only do this at link time, you've got, LLVM is enormous, right? If I'm trying to compile LLVM, this already takes a ridiculous amount of time. If after that I have to gather up all of the object files and then go through and analyze all of the class hierarchies, how much time, what am I actually paying at compile time to get these performance benefits?
As for the compile time, actually, it depends on the link time optimization type. For example, in the full LTO, which is a monolithic link time optimization, we will get like because it is not scalable. So before our optimization, it's like when we compile the Chrome project, it takes 4 hours, like, and then apply our optimization into you need to pay more, like 10 minutes. It's like it's not too much, but if you but currently that actually the single LTO is the more is the better option, which it is non-scalable. So we actually evaluate a little bit the compile time. The compile time overhead is less than 2%.
So this is the overhead over once you're already doing LTO.
Yes.
But if I compile this thing without using LTO versus using LTO so that I can do this like dynamic cast optimization, do you have some insight on like how much worse that is? How much slower that is to compile?
I think it depends on your project, how large your project is, and how many cores in your computers. For example, a single LTO it can be parallel linking. It's about parallel linking. So if your computer has a lot of cores, then it can parallel linking many tasks. So I think the build time will not increase a lot. But if you use full LTO, yeah, it's maybe your compile time will be doubled or tripled. It's not good.
Okay, all right.
Great, thanks. We will thank you very much for the talk and the engaging discussion. And let's switch over to the next speaker, and let's thank the speaker again.